either the horizontal or the vertical. And I made it emphatic that it is always easy. It's the same. You're going to get the same things. Always use it easy to use the same constant angle, just like a refreshment of what we looked at. We looked at something like this. We have this force, okay, maybe F1. I'm not going to use value now. Then we have theta here. We have another force
I'm
in
not seeing the screen,
position.
sir.
You're not sharing screen?
Yes, sir.
Oh, I'm sure. I thought I'm sharing screen. Yes, I'm sharing. Can anyone see my screen? Because I know I'm sharing screen. I'm sharing the entire screen.
Thank you. I can see it.
You can see my screen. So, Mustafa, what's going on? I'm sharing screen. Let me reshare. Let me stop and then reshare the screen. Oh, I can see Mazida now. You're welcome. Many Hussein and Dean. Mustafa, are you
Sir.
seeing my screen now? I'm sharing screen now. And then I'm sharing this.
Yes. No, sir, I'm not seeing it.
Okay, good. Then I said I'm trying
I'm
to
not
ref
seeing it.
you're not saying
Yes, sir.
There's nothing wrong with the
what's
screen.
going on. Are you using phone or laptop?
Phone.
Whatever you're using, you should be saying that I'm sharing screen. I'm sharing screen.
Maybe I should rejoin.
No, please. Okay,
He
you
should
can.
leave and come in again. The issue should be from his end, because it
Okay,
is
okay,
quite visible here. So maybe it's his network.
okay.
We
Maybe you
can see
can
the screen from this end.
exit and coming back immediately. I'm going to wait for
Yeah.
you. Exit and come in immediately, please. Okay, Mustafa, can you see my screen now? I'm sharing a whiteboard.
Yes, I can see it. I'm seeing it now.
Good. Okay, no problem. So I mentioned the last time that if you have, we are resolving to two perpendicular planes. Two planes can be perpendicular. It's not composite. It has to be vertical or horizontal. But when vertical and horizontal planes meet, okay, let's plane now. I mean axis. Now, when they meet, the angle in between them, this is vertical, this is horizontal. The angle created in between the two vertical and horizontal is 90. So they are perpendicular. So it's not composite. It looks like that, and a line may go like this. If another one cross it perpendicularly like this, angle in between them is also 90. So our interest in this topic is to find all resolution along two perpendicular planes. So we have chosen to use horizontal and vertical planes as our point of reference. Okay, so let's see. Now this force F1 is naturally horizontal, so we don't need to resolve it to any other place again. This is also horizontal. This is F2. We have here F3, and then at this vertical I have F4. For example, F4. This is F5. F5. Okay, let me put another one here. F6. F6. Making angle. This is theta. Okay, let me put this one alpha with the negative horizontal. And I told you something again. I said when resolving, it is in your normal graph that you have direction of the east like this as positive x, and this direction negative x. This is positive y, this is negative y. I said ordinarily we can choose anywhere to be positive and anywhere to be negative. If you have chosen a direction to be positive, anything going against that direction is negative. So here now, if we are resolving forces to the horizontal, we are only going to consider forces naturally vertical, forces neither horizontal nor vertical. Any force that is naturally vertical, it does not have components on the horizontal. So when considering horizontal resolution, we consider F1, consider this F1, sorry, we consider this F1 and then F2, F2, if I'm resolving, I choose direction. If I say resolving horizontally in this direction that you always take as positive already by yourself, then anything positive, anything going in that direction will be taken as positive, or anything that I can resolve to that direction will be taken as positive. Anything in the opposite direction that is going this way, this arrow, will be negative, and anyone that flow naturally can resolve it to the horizontal, and that is the closest horizontal to it, will also be considered negative. So if I'm resolving now, F1 is going to be positive because that's even the one going naturally in this direction. So I'm going to have F1. Okay. F2 is also horizontal, but in the other direction. So I'm going to say minus F2. Now, will I consider F4 and F3? No, those ones are naturally vertical. So their resolution on the horizontal is 0. The resolved part of F4 on the horizontal is 0. The resolved part of F3 on the horizontal is 0. In the like manner, the resolved resolution of F1 to the vertical is 0. Resolution of F2 to either the vertical up or down is going to be 0. But forces like F5 and F6 that are neither vertical nor horizontal, what did I tell you last time? I said they are going to have resolution on both axes. F5 can be resolved to the horizontal. If a body is moving horizontally, if the body is moving horizontally and it is due to this force F5 that is causing the horizontal motion, then it is not this as it is like this that is causing that motion. The resolved part of this on the horizontal axis will be the one in term right riding it horizontally. So if we are using, we are still going to look at those values. We are using that Newton's law of motion, F equals to ma. So if a body is ma, if a body is moving along the horizontal direction like this, then if and these forces do not exist, F1 does not exist, no force exists other than maybe look at this diagram now. This is a mass and is being pushed by this force ordinary F at an angle theta to the horizontal. So this is a mass. So if you are told that the body moves through a distance x to this point, distance x, okay, so and you have to find work done by F. Work is force times distance. Ordinarily work is force.
And the
Work
distance.
Work is force times the distance moved in the direction of the force. Now, because it is moving horizontally like this, we cannot use this value. If this value is 20 Newton, we cannot use it. We have to resolve it to this side. So we write this horizontal side as F along the horizontal, Fx. So instead of writing F work is equals to force times the distance, we write force along the horizontal axis times the distance horizontal distance moved. So if the body is moving vertically like this, I'm going to erase all this now. We are going to have a force along the y-axis that is making it to move vertically in a particular distance. So we won't use this force 20. We will use the resolved part of F along the vertical, then multiply by the distance it has moved vertically. Okay. So let me clarify this now. Then we'll have once we try to get to, if we can get to moments. So I'm resolving horizontally in this direction that I have chosen. So F1 is in that direction, so that's why it is positive. I'm not showing the plus. Okay, minus F2, which is naturally horizontally. Now I'm going to consider F5 and X6. Okay, what did I call the resolution of F4 along the horizontal? What did I call? Who can remind me? F4 along the horizontal.
F4 is
Zero.
positive.
0, because it does not have any effect there.
Yes,
We
sir.
can resolve it. I can show that, but okay, don't worry. Let's see. I told you now I'm going to show you why F4 and F5 are going to be 0 along the horizontal. I'm going to show you now so that you see. But first, you need to see that the angle in between vertical and horizontal is 90. So the angle we are going to use in that resolution is going to be 90, but I'm going to show you later now. Now consider this F5. Now, I told you that our resolution can either take sine of the angle or cosine of the angle. Just try to detect one. Okay. Now we want to resolve this F5 to this horizontal. So let me use a dotted line to complete this triangle. This is a right angle triangle now. And I told you that this vertical here, consider it as this vertical line here that is standing. Okay. Now if we want to resolve this f, this is the f5, this is the line of f. I want to resolve it along the horizontal or the vertical. You know that SOHCAHTOA, sine is opposite. Sine is opposite of hypotenuse. Sine is opposite, and then cosine is adjacent. I'm just doing CA. This is SOH. So if this angle theta is facing, look at this vertical now. This is a vertical line. This angle theta is opposite to the vertical. Opposite to the vertical. So anytime I'm resolving this vector 5 or force 5 along the vertical, I'm going to use sine. It's going to be f5, that value f5 sine of angle, this sign that is making with this. Then this horizontal, if I want to resolve this same f5 along the horizontal, what is the position of this theta to the horizontal? Is adjacent. If this is opposite, this is hypotenuse, and this is adjacent. Adjacent is always cos. So I'm going to write f5 cos theta. Now, if I resolve it, where is the closest horizontal to this f5? This is the closest horizontal. Closest horizontal. If f5 have along this part, had been along this part, I will have resolved it to this other horizontal. I'm going to be negative because that direction is negative. Now I'm resolving it to this horizontal, which is positive, so I'm going to write plus. Now resolving vertically, theta is opposite to vertical, so that is sine. Sine uses sine. Sine uses opposite. Cosine uses adjacent. So horizontal is adjacent. So I'm going to use f5. Try the f5 first. f5 cosine theta. Yes, I'm going to resolve this f6 again. F6, use a dotted line to complete this. This line is vertical, right? What is this theta, this alpha, this angle to this vertical? Opposite. So if you are resolving f6 along the vertical, it's going to be f6 sine theta. So the closest horizontal to this f6 is this negative horizontal. So, and it is adjacent to the theta. So I'm going to use cos. So it's going to be minus f6 cos alpha. Sorry, this is alpha now. So if a direction has taken cos, then the alternative direction will take sine. So if I want to resolve vertically now, I told you it's not compulsory to use up. I want to resolving vertically, but I'm taking the downward direction as positive. I made the conclusion last time that if you resolve along a particular direction and the total addition and subtraction of, you do f1 minus f2 plus f5 cos theta minus f6 cos theta, if the answer you get, for example, is now minus 10 Newton, then you know that you are going to change it. That you have to say, therefore, resolving all those forces in this opposite direction would have given you positive 10. And we are going to go for the positive 10. We cannot decide which direction will be positive now. So this is how to find the net, or what we have found now is the net horizontal force, the total horizontal force acting on the particle. So now let's find the total vertical force. I want to choose the downward direction as positive. So anything going upward or anything I can resolve upward is going to be negative. So where will I start now? Where is the force pointing vertically already? F4 and F3 are vertical, but
how do you get f6 cos theta in that other place?
F6. Okay, let me take this again. Do you understand how I resolved F5 to become F5 cos theta? Do you?
No, sir.
What was the explanation behind that? I'm going to say it. I just want to give, if you can know it, you know this. What is the explanation why F5 becomes F5 cos theta along this horizontal? What? Quickly. I'm going to say it if you don't know it, because I believe you do not know it. That's why you're even asking for this. Okay, I'm going to say it again. You want to try? Do you want to try, Mustafa? Do you? Do you know the reason why F5 on the horizontal becomes F5 cos theta?
No,
So
sir.
no, yes,
No, sir.
you do. Okay,
No.
why?
No, sir.
Are you saying yes or no?
No,
Okay,
sir.
okay. Now let's listen to the explanation. Are you familiar with SOHCAHTOA?
Yes, sir.
Yes,
You are
sir.
familiar. So what is SO? SOH. Sin theta is what? SOH. What does that
Of
mean?
hypotenuse. Opposite of hypotenuse. Sine opposite of hypotenuse.
Sin cos theta is CAH. What is that? Adjacent over hypotenuse. So look at here now. It's okay. I wrote SO only. I did not put H for sine. I wrote CA only. I did not put H. Okay, this is the hypotenuse. Hypotenuse is the longest side of a right. If I look at this right angle triangle now, this is a right angle there. This is the right angle sign. This side facing it, this side facing is the hypotenuse. So we are not talking about hypotenuse now. We need, where is the opposite? Look at, this is the opposite, right? Of this, look at this theta. Opposite means what is facing it, what is directly facing you. Now look at this theta. No, not F5. Actually, F5 is actually this line. There's no space for me to write. That's what I'm putting there. Let me put it there now. Let me clean it from that place. Let me put it where it's supposed to be. F5 is not vertical. F5 is this line itself. F5. Okay. F6 is this line itself. This line going like this is F6. So that is F5. F5 is along the hypotenuse. Okay, that's the line itself. F6, I might be writing it at the edge, but it's representing this line, this length. Okay, so nothing is on the vertical, nothing is on the horizontal. Now I'm not telling you this theta. Where is the side that is facing it? Is it not this vertical? Then Mustafa, respond. Is it not this vertical that is opposite to this theta?
Yes, sir.
Yes.
Yeah, so if you are resolving this slant, this bent vector, this line that is neither vertical or horizontal, the horizontal that I'm supposed to take it is I'm supposed to push it to this vertical here, this vertical side. I'm supposed to find the resolution on this vertical and then find its resolution on this horizontal. But I'm telling you, this vertical, see it as this vertical line that I've drawn here. In vector, we consider it like that, this vector, because I can complete this to under vector law. Triangle law of addition of vectors or parallelogram law. Opposite sides of rectangle are the same. Opposite sides of parallelogram are the same. Okay, let me clean this part. So this vertical line you see here, that you are supposed to resolve this vector to, we are supposed to resolve it to this vertical and this horizontal. Okay, we are considering this opposite. This opposite is the same thing as this vertical. So if this theta is opposite to this, sine is the one using opposite. Sine is opposite. So this theta, this vertical is opposite to it, is facing it. So this side is going to be F5 sine theta. Automatically, this horizontal, look at this, theta, this is opposite, this is adjacent. This adjacent is going to be this F5 cos theta. If one has taken sine theta, F5, so when I'm considering horizontal, I'm going to take this cos theta. Just note it like that. Let's find this part also before we go. Now, look at this angle alpha. This line that is vertical, is it opposite to this angle or it is adjacent to it? Only Mustafa should respond. Look at this vertical line. Vertical line. Is it facing this angle?
I say I don't understand it. It's not Mustafa.
Oh, sorry. Who said he doesn't understand? Then,
No.
okay, whoever that doesn't understand, I'm asking you now. This angle alpha, you are the one I'm asking. What is this vertical to it? Is it facing it? Is it opposite to it?
It's facing it.
Facing it. So facing means opposite. So anytime it is opposite, you are resolving vertically, you must use F6, that vector you are resolving, sine the angle facing it. So vertical resolution of this vertical is going to be F6 sine alpha. But it is now going to the negative direction. That's why I'm using minus F6 sine alpha. So if this is opposite and is sine, then this horizontal is going to be cos. And I'm resolving horizontal. That's why it's going to be F6 cos. Let me write it here. On this horizontal is going to be F6, okay, cos. What is the angle? Alpha on the horizontal. Why? Because this horizontal is the adjacent to this angle. Adjacent is always cos. Opposite is always sine. The opposite is vertical. So when I'm dealing with vertical, know that this is going to be sine. I've already written cos for adjacent. Does it clarify that? Who is that? Is it Dane or Zain? Whoever that does not understand. Okay, let's go now. I
take cos,
Okay.
the other take sine. But this two is taking cos.
Horizontal is taking cos because the angle is adjacent to it. I'm going to show another diagram so that I don't think horizontal is always cos and vertical is always sine. No, that's why I'm not using horizontal. I'm using opposite and adjacent. Look at this, for example. Now, look at this vertical and this horizontal, so that you know. I'm putting my theta here now. Theta. I'm putting theta there now. I'm not putting theta down here. No, I'm putting theta that's up. So this is vertical axis. This is horizontal axis. If I'm considering this theta, this is the theta. Complete this triangle like this now. So where is the opposite? Where is the opposite to this theta? This line that is horizontal. You can see. So what matters is if it is opposite to the angle, you are going to use sine. If it is adjacent to the angle, you are going to use cos. So do not cram it by saying horizontal component is cos, vertical component is sine. It depends on the angle. Now I'll put the angle here now. So this,
Sir,
yes.
the angle facing that theta, the angle facing this horizontal line.
Yes, this diagram now.
Yes,
This is
that vertical line you just drew there. Is it cos, Abby?
No, just listen. I'm going to explain. That's what I'm explaining now. Now, look at this diagram now. I want to resolve this force. Let me put it. This is the force, actually. This is the force. I'm calling the force of magnitude F. This is the horizontal. Sorry, this is the hypotenuse of this right angle triangle. I've completed this triangle now. If the theta has been here, I will have completed the triangle this way. But theta is not there. So I'm completing the triangle at this other side. So now, where is the side that is opposite to this theta? It is this horizontal. The opposite means sine. So it's going to be F sine theta. And see, horizontal becomes sine here. Automatically, this horizontal is going to be cos, because this vertical is going to be cos, because this theta, if this is opposite, this is the adjacent to the theta. So this is going to be F cos theta. This vertical here is the same thing as this vertical here. This horizontal here is same thing as this horizontal here. So I can put F sine theta here. This is the vertical. I can put the same value here, F cos theta. You can see vertical becomes cos, horizontal becomes sine. So I'm not saying it in terms of vertical being sine or horizontal being cos. No, I'm saying it with respect to the angle, to the side opposite to the angle. If this is the angle, this is the side opposite to it. Opposite is going to use sine. And then this is the adjacent. Vertical is not the adjacent, so it's going to use cos. This vertical is this vertical. This horizontal is this horizontal. Please, let's move ahead, please. Just know that sine, SOHCAHTOA is what we are using here. Opposite to the angle, you are using sine. Adjacent to the angle, you are using cos. Okay, so looking at the diagram, I'm resolving vertically, and I've chosen the downward vertical as positive. So what is pointing downward vertical already will become positive. So this is going to be F3. There's no sine or cos for that. Now, which one is naturally vertical again? It is F4. Sorry, this vertical here is F4. Let me clean it for where it is here. That vertical is F4. So it's going to be minus F4, because F4 is going upward. I'm choosing downward as positive. Minus F4. Okay, so what are the, sorry, F4, not F2, F4. So what are the other two forces I'm going to consider? I won't consider F1 because F1 is yes, horizontal. F2 is naturally horizontal. I'm going to consider F5 and F6. So do not disturb yourself. What is the resolution here? For F6, here is F6. The horizontal has taken cos. F6 cos theta. Automatically, the vertical here is going to be sine. If one has taken cos, the other will take sine. If one has taken sine, so I don't even want to bother. But if I want to bother, look at this now. This is opposite. This vertical is opposite to the angle. Opposite is sine. Now, where can I resolve these two? The closest vertical to it is the downward vertical. I cannot take this vector F6 and move it up. If I move it up, that is going to be negative. Okay, but that is not closer. The closest vertical to this line F6 is this downward vertical. So downward vertical takes positive. So it's going to be plus F6. Now, what did I say is going to take? Sine or cos? Vertical is opposite. Is facing the vertical.
Fine.
The sine, the angle, sine alpha. Sine alpha. Sorry, this is sine alpha. Then I'm going to consider F5. look at F5. I've already written it. Opposite is F sine because horizontal adjacent is what? F cos, F5 cos. So the vertical is what I'm considering. I'm going to use sine. But this F5, the closest vertical to it is this direction of F4. And that upward direction is going to be negative because I'm resolving downward vertical. So I'm going to be minus what? This is the resolved part on the vertical. F5 sine theta. F5 sine theta. F5 sine theta. This is the net.
Theta, not alpha.
You say what?
Theta, not alpha.
Oh, thank you very much. Theta. That means you are following. Theta, not alpha. This because this is just along the vertical. Question might come. Don't always go for the total resultant. Question might say, what is the net horizontal force acting on the part? They've drawn all the forces. They're not asking for what is the net horizontal force. Please do not consider the vertical resolution. Just resolve all forces along the horizontal, and then the result you pick any result that is in line with that. If you find the total horizontal, we are going to consider two horizontal planes. I've considered this downward vertical, Abi. So this is downward vertical. Sorry, that is downward vertical. What is horizontal? I considered to the right. I considered this. So to find the total resistance, I start from anywhere. If I want to start from vertical, I start from vertical. Vertical is downward. And say I want to start from this horizontal. So I draw this horizontal force. The value it gives me, I put it there. Net horizontal force. This is downward. Don't come and start it from here. No, let's start it from that. But start it from where you stop here. You are stopping at this arrow. So this tail of this vertical, bring it here. Okay. Then complete the right angle triangle. This is total vertical force. Then the resolution, this line here is going to be the total resultant of horizontal and vertical. Most time, this is what we use, the resultant. But if question is not asking you for net horizontal force, consider the total horizontal here. Find the answer and move on. Let's see an example. I have a jump. Where did I put it again? I have a jump question exactly that I shared with one of my students. You shared it with me actually. I saw it somewhere. Where did I keep this? Okay, let me draw a random question. Question that looks like that one. Don't know where I put that again. This 12 things. Okay. 9 newtons. Make it an angle. Sorry. Let's use that case. And then this will have 11 newtons. Okay, who can find for me the net horizontal force? Net horizontal force. You can always use, since there's horizontal, but you can always use the vertical dotted line to show vertical here if you need. But let me erase it. The question does not put this. Question does not introduce anything vertical. So here I'm asking you not the total resultant of the forces. I'm writing the net horizontal force. Net horizontal force. You want us to do this together? I should leave it for you. Net horizontal force.
Let's do it
Just so that
together.
let's do it together. This is going to be confusion. This is vertically. We are not considering it at all. What are the vectors you are going to consider? Vector of force 12 newtons, 11 newtons. Are they the only two we are going to consider on the horizontal? Are they the only two?
Yes, sir.
Yeah.
With 9 newtons.
9 newtons. The resolved part of 9 newton on the horizontal, not just the 9 newtons. The 9 newton is neither vertical nor horizontal. That makes it have components on both vertical and horizontal. But the question is now asking us for total horizontal force. So I want to resolve in this direction. Resolving in this direction, as I'm saying, this is going to be 12, which is in that direction already. 11 is against it, minus 11. I'm now going to consider 9. Okay, now let's do this together. You are telling me what I'm going to do. Draw this perpendicular. So this is a right angle triangle. Now, the vertical component of this is opposite to, is going to be 9, because it's opposite, 9 sine 30 to the vertical. This is vertical. Automatically, horizontal is going to be this 9 newton. It's going to be this 9 cos 30. That's the horizontal. And it is closer to the direction of 12, which I've chosen to be positive, also plus 9 cos. Now, is it Dane or Hussein? Why am I using 9 cos 30? Do you know why? Why is it 9 cos 30? Is it Hussein that asked me that question, or Dane? Who asked me that question then? Okay, anybody, quickly.
It is
Let's
Hussein
put this
now.
value.
Hussein is the one
Hussein,
asking questions.
Hussein, are you there? I'm
Yes,
asking you, why have I used 9 cos 30 here? Can you explain to me?
because the question already take 9 sin theta.
Uh, that is part of it, but what is the original excuse in terms of SOHCAHTOA? Yes. In terms of SOHCAHTOA, yes. What is the original excuse? The reason, I mean. Because who can help him? Who can help us?
Because
Anybody should speak.
the opposite over hypotenuse. I'm sorry,
Because we
adjacent
are
over hypotenuse. We are giving
adjacent is okay. The 30 degrees is adjacent to the horizontal. This horizontal is the adjacent. Okay, and adjacent to the theta is going to use cos. This vertical line here is facing or opposite the theta. That is going to be sine. So let's put the value 12 minus 11, that is 1, plus 9 multiplied by, I've told you how to find 30 degrees, 60 degrees quickly. So if sine 30 is 0.5, what is cos 30? I've told you. What is cos 30?
0.8.
860. Thank you very much. So 1 plus 9, 9 times 0.860. What's that? Plus 1. Give me the total addition, and that's going to be the net horizontal force. So I'm now going to leave you all to find the total horizontal, and then we move to something else today, because I'm preparing to put the elementary part of it in your test. Which you say, have you added? I'm very sure this is Mazida. Is that correct? Is that Mazida? Yeah, Mazida is always the one helping me with calculator. 8 point. Give me again. 8 point.
794.
794 or 094.
794.
794.
I got to.
79. Let me just do it. 79 newtons, or approximately 8.8 newton. This is the net.
Somebody is getting another answer.
Oh, so please,
Let's
who
other
is
confirm.
some other person?
So I got 8.66.
Even me, I got 8.66.
You got 8.66.
Yes.
Now maybe
I got
Mazida
8.66.
has not added. Now, Mazida, the answer you gave me 8.79. Is it for 9 times 0.866, or you have added 1 to it?
I've added one.
Let me confirm myself. I'm not always calculating this phone. Okay. Please, it matters for you to check whether your calculator is in degrees. You know, this is cos 30 degrees. So you see a letter D. Letter D. Maybe I'm going to screenshot my let me screenshot this. This is let me screenshot this and send it to the page. So that this is what you're going to be always seeing. Let me find this answer first. 9 cos 30 degrees. That is 7.794. If that is what you have. So if I add 1 to this, it's going to be 8.794. Mazida is correct. Oh, now you all of you getting different answer. Let me screenshot this and send to the page. Let me use my phone because I'm using laptop for this. This is what you should always be looking for. You all should check this UTME page now. I'm going to settle it. My own is showing full letter DEG to show degrees. Okay, check this now in WhatsApp group. Check for that. Some calculator will put it as ordinary letter D. It means degree. The angles can be in degree, radian, or grand radian. DRG. You'll see DRG. Your calculator will show something DRG. Always make sure it's in letter D. My own is showing it DEG to show that it's in degrees. It can be in R. You can be saying R. You can be saying G. So make sure you are saying D at the top. So that D means degree. So any angle you are pressing is 30 degrees. So if you are getting a different answer, it's either you have computed it wrongly or you have actually done the right thing, but your angle is not in degrees. Please confirm that and then do this. You need to get this, please. We'll move on. We'll move on now. Please, have you confirmed? I want all of you to redo that and get 8.9. Have you all correct? Have you all gotten that now?
Tony, I got it.
8.7942. Yes. So that shows degrees. That matters very well. So now we want to find, this is the net horizontal force. Now to now find the total resultant, we need to also find the net vertical force. When finding net vertical force, we are considering only two vectors. What are the two vectors we are considering? Anyone want to find net vertical force? What are the two forces we will consider?
8 and 9.
8
Like
and
that.
8
Why
and
don't you
9.
just
Thank you very much.
vertical?
Thank you very much. I want to resolve vertically. I'm choosing this downward as positive. So that 8 Newton is going to be positive. So it's going to be 8. Then because this 9 Newton can only be resolved to this part here, vertical, and that part must be negative because it is against my direction. So I'm going to put minus first. Now, when I resolve this 9 along the horizontal, it was cos. Automatically, this is, okay, I can see this angle is opposite to it. So it's going to be 9 sine. This value is now 9 sine 30 along 9 sine 30 degrees along the vertical. So it's going to be minus 9 sine 30 minus 9 sine 30. So this is going to give 8 minus, what is sine 30? 0.5, right? I told you whenever you are multiplying by 0.5, it's going to reduce the number to half. This is 8 minus 4.5. What is 8 minus 4.5? 3.5 newtons. This is the net vertical force. If I had resolved this way, I only choose upward. If I have resolved this way, vertically upward, I will have gotten the same as upward that goes that way. It's going to be 9 sine 30, 4.5 minus 8. That would have been negative 3.5. You can see. So if I had chosen that direction as positive already, my answer would have been minus 3.5. So I'm going to say, therefore, resolving downward vertical is that same value, but delete the minus. If resolving to the left is minus 4 newtons, automatically resolving to the right is going to be positive 4 newtons. So I've seen my two nets now. The directions are like this, downward, and then downward, and then which is direction? This upward. So these directions, downward gives 3.5, and this gives what? 8.97. So where should I start from? I can draw two right angle triangle. If I want to start from vertical, which is this, draw vertical here.
So it's 8.79, not 97.
Thank you. This is the vertical 3.5. Then at the end of this, that's where you're going to start the horizontal and in the direction. And you can see that should be longer. It should be longer because the value is bigger than this. Vectors in magnitude. The line, you see, vectors have magnitude and direction. The line is what we are using to represent the magnitude.
Diagram. Please come again.
That's who? That's Mustafa.
No, it's
Zain or Hussein. Okay, now look at our direction for the net horizontal force. This question is actually net horizontal force. So we are supposed to stop here. This is the net horizontal force. It's 8.79 newtons. So what is the direction of that? This direction, right? Come and see it here. I'm using this arrow to represent them. This is the direction of the 8.79 newtons. What is the direction of the vertical, the net vertical? Downward, and it is what? 3.5. I'm using this arrow to show it. The direction of the downward, the total vertical is 3.5 newtons. So this, according to the question, this is just our answer. 8.79. They say find the net horizontal force. So we stop. But I want to find the total force acting on the particle. That's why I'm finding the net vertical also. Then we combine the two using right angle triangle. And Pythagoras theorem solves that. So to draw that, here is it. I'm starting from this vertical, which goes this direction. So the thing is, you must start another vector. Vectors have head and tail, just like an arrow. This bow, this arrow and bow, this symbol, this one we used to. This is the tail. This is the tail of the vector. This is the head of the arrow. So this is the vector. In physics or applied math, we use line, the arrow, to represent the magnitude. Vectors have magnitude and direction. Then this arrow head is the direction. This is the direction, and then the length of the line is the magnitude. So if we have two vectors, such as forces are vectors. One is 3 newtons and the other is 5 newtons. And they are pointing, they are going in the same direction. If this is the 3 newtons, okay, then let the 5 newtons be longer. The length represents the magnitude. We call it vector length. So the length is the magnitude. Show that this one is 5 newton. Where is the direction? The arrow pointing towards the east. This is the 3 newtons. So this is how we show that in diagrams. Okay. So when drawing combining vectors, okay, you start another vector by putting the tail of the new vector at the edge of the vector you drew last. If there are, we are dealing with two vectors now. This is the vertical. I've drawn the vertical this way downward. So this is the tail where I'm starting from, and I end at the head here. This is the head. Now the horizontal vector that goes this way, this is the head, this is the tail. I'm going to put this tail here at this edge and then draw it like this. If there's another third vector again that goes this direction, this is the tail, this is the head. This tail, I'm going to put it at this edge and consider that it is moving like this. I draw it like this. That's how we combine vectors. We put the tail of the new one to be attached at the end where we stop, at the head of the last vector drawn. Is that clear? Now, these three vectors, although I've not mentioned this before until we start equilibrium, if we can be such that if three vectors are drawn, okay, if we are now rearranging them, if they can be such that they can form a closed figure, then the vectors are in equilibrium. If our rearrangement gives a total diagram that is not closed, then the three vectors or the number of vectors you are combined, they are not in equilibrium. So equilibrium starts with what is the smallest diagram you can have that is closed? The smallest diagram you can have that is closed is a triangle. It's a triangle. Let me remove this. Although, let me leave that now so that we have to combine so many things. Condition of equilibrium is that if I can draw another vector to this, sorry, that can close this. Now we have drawn the total vertical. Oh, we have drawn the total vertical in this direction, and so this is 8.977979 newtons. So these two forces are not in equilibrium because they are not closed, they are still open. But the total resultant is going to close it. Look at the direction I'm going to put the total resultant. You can see the first arrow goes like this, then the next one follows it in different, but the arrows are following themselves. If another want to go up, it's supposed to go like this so that the arrow are following themselves, not turning back. This arrow goes down, this arrow goes down like this. You can see this arrow goes like this, and this one goes like this. Okay, but the resultant will not go in their direction. We counter their direction. Instead of me to have this arrow following their direction, the resultant is going to counter it like this. So if you are going downward, you face this way. You can see you're supposed to face this way, but the resultant comes this way. So how do we start drawing the resultant? Where is the tail of the starting vector? This is the tail of the starting vector. Join it to the head, H-E-A-D, of the last vector. So in that direction, look at the direction I'm coming. So that is going to be the direction of the resultant. Anything that counters that, we call it equilibrant. When we start Newton's equation, we are going to show you that equilibrant and resultant are the same, opposite and equal forces. They are in line with Newton's third law of motion. If you are taught to find the resultant, you just want to see it in diagram. Here is it. They might be drawing different diagram. They'll draw on that right angle triangle. They'll put this like this, put this like this, and then put arrow like this. This is not longer equilibrium because equilibrium does not follow the direction of its coming. It counters the direction. This one is going down, then it turns to the east, then it's supposed to turn like this, okay? It's supposed to turn, the one that turns in that direction is called equilibrium. The force needed to bring the system of forces already available to equilibrium. Okay, that is the equilibrium. But they might ask you to find equilibriums. Do not disturb yourself. Equilibriums and resultant have the same magnitude. What matters is they are just in opposite direction. Look at the direction of the resultant now, coming like this, from the tail of the starting vector to the head of the ending vector. But the resultant, the equilibrium will go the other way. So they have the same. If you use Pythagoras theorem, we are going to get the same magnitude. Okay, so let's use Pythagoras theorem now. You should be familiar with Pythagoras theorem. So r squared equals to 3.5 squared plus what? Plus what? Let me know whether you are familiar with Pythagoras theorem. Plus what?
8.79 square.
8.79 square.
Okay, 8. Thank you. 8.79 square. Find this for me, please. Oh, sorry, 79. Square both of them and give me the actual answer. 3.5 squared plus 8.79 squared. Add them together, then we know we are going to find square roots of both sides. So ordinary R will be the square root of everything, the summation of the squares. All of you should attempt it. I'm going to listen to your answers differently, not just Mazida. It was Mazida that assisted us throughout in last class. Please, have you gotten the reason why we have 8.9? All of you, please, that degree matters. It matters. I'm waiting for this answer. 3.5 squared. Okay, let me also do this.
So the answer is 9.5119.
What are you saying, please? 3.5 squared plus 8.9 squared. The total, what is it? I want to put it under this square.
89.5141.
89.5141.
5141. Thank you. So when you find the square,
89.544.
thank you. All of it will be getting this. I do not need to confirm again. So the square root of that is R. What is square root of that?
9.4612.
9.46.
4612.
One is one following it. So this is the net horizontal force. This is the value of the resultant. This is also the value of the equilibrant in terms of magnitude, but they are in opposite direction. If resultant is going up, equilibrant is going down. If resultant is going to the right, equilibrant is going to the left. And this is alternative way of showing. Let me show you now. If angle of let me show you something now. Let's find angle. Now, these are vectors. They have both magnitude and direction. Ordinarily, we can represent this in two ways or three ways. We want to show how we can put the direction. What is the resultant? What's the resultant making with the horizontal? What's the angle? Call it theta. Then SOHCAHTOA. This is where we now use tangent. Tangent is opposite over adjacent. So tan theta. Tan theta is what? Tan. Please make sure your I'm going to confirm it. I'm not going to. Tan theta equals to opposite, which is opposite is 3.5 over adjacent 8.79. So you're going to get a fraction here, 0 point something. Then to find theta, you know how to find that. Theta is going to be inverse. We call it arctan, or tan inverse, tan to the power -1. How do you press that? Second function or alt. It depends on your calculator. Let me show you something now. You are going to be checking column. Some people think it's always second function, or some people think if it is shift written in your calculator. Sometimes this is what you check for. Let me screenshot my this and then show you something. You are going to be checking color. Let me show you something here now in the WhatsApp. If color written, on top of sign, if it's check sign, they're going to put sign raised to power -1. What color is used in typing that? Is it red? Go and check which button is in red. Is it second function that is red? You have to press second function, then press sine. It's going to show you arc sine. Sine raised to power minus 1. So if it is yellow, which button is if they write it in yellow, I want to show you my own so that you discover what I'm trying to say here. WhatsApp. Okay. Let me show you my own. I'm sending this. Aha. Let me color this now. Look at my own is alt. This calculator is alt. Then put either second function or shift. Now, anything you want to press, all those buttons that have, look at this. Arc sine with yellow, sine raised to power, tan raised to power. Anything yellow, you must press that alt first for me. Okay, so let me send this to the WhatsApp and everyone should look. You can see, please look at the WhatsApp. For sine, look at sine. Sine type on the button with black, but above it is sine raised to power minus 1, which is arc sine. But the button up here is alt, A-L-T. It's in yellow. So if you want to press sine, arc sine, you must press that yellow button, then press yellow. So your own might be showing second function and 2NDF or shift. So the color is what matters. Now shift is in green. If I want to press, if you're looking at WhatsApp, if I want to press anything that have green, that is above, look at this backward arrow. If I need it, what is on top of it is a ENG. So before I press it, I must press that green button first before I press it. So that it is color that you check, not just conclude that it is either second function or shift. What's the answer, please? Arc sine.
21.70.
What did you say?
21.70.
Okay. So the first thing you are supposed to do here, because although you are not interested in, is going to be I don't know what you got by dividing this 0. Whatever.
I got 0.3981.
Again
0.3981.
3981. Thank you, Mazida. So and this is 21 point what?
70.
7. Is everybody following? Let me leave it. 21.7 degrees. Please, who is getting this with Mazida? Please, who is getting this with Mazida?
So I got the same thing.
You got the same thing. That is Dean, right? I've not
Olamide.
memorized your Olamide. Please, Dean and the Mustafa. Are you along the same? Are you getting the same thing? Okay, now
So I
now
got 0.3995, but then I got 21.7.
Okay, good. So now look at the position of the theta. That's the direction, Abi. This is now what is now the value of the resultant. We can write this in so many ways. The first way is to use the theta direct.
Why are we using tan?
You say what?
Why are we using tan? Tan.
Thank you very much. Who is asking me that question, please?
Uzain.
This is actually mathematics. Okay. Now come to this side. Are you familiar with SOHCAHTOA? That's the first
Yes,
question.
sir. Yes,
Are
sir.
you sure? Tan
Yes,
theta
sir.
is what? Tan is what? Tan is what?
Opposite over adjacent.
Toa. Okay. Now, use your cursor. I don't know. Okay. Now, show me which number is opposite to this theta, which number is adjacent to it, and which number is in the resultant. This is the resultant, which is the hypotenuse. What number is in the opposite? Please tell me. What number is in the opposite to the theta?
0.5 is opposite, while 8.79 is adjacent.
Adjacent. So what? Yeah, you said opposite and adjacent. So what between sine, cosine, and tangent is talking about opposite and adjacent? Which one?
Sir, I already understand, sir. Thank you, sir.
Okay, thank you very much. Now, so next time I'm going to be making you guys to be answering your question by yourself. So now, if you now follow that, do you now understand how to use Pythagoras theorem in getting the total resultant as well?
Yes,
Thank
sir.
you very much. Thank you very much. So we got arc tan of that angle to be this. Now I want to refer something to it. Now the theta is this 21. You can see the theta here. We can write resultant in two ways. The first way is to put it like this: r, theta. R is the magnitude because it's a vector. Theta is the direction. So what is r? 9. Oh, what's the value again? Let me move up. What's the total resultant? 9.46 newtons. 9.46 newtons, comma 21.7 degrees. This is it. We can put it r theta. They usually put it in brackets, and x comma y, so r comma theta. So it's going to be 9 point something, 9.46 Newton, comma 21.7 degrees. Alternatively, you can use, if you are dealing with bearing in your math, we can also have not theta degrees to the east, or we have not theta degrees to the west. We can either start from north or south. This is north, okay, this is south, east, and west. So if the final stuff is here, and this is the theta here, so this angle is going to be south theta degrees to what direction? To the direction of the east. It's going to be south theta degrees east. If the angle was here, okay, and theta is right here, for example, if theta is here, theta, we don't start from east, theta degrees north. We have to start from north. So how do you get the angle here? You're going to say 90 minus this theta. So if theta was 40 degrees, then the angle that was going to be here is going to be what? 50. That is 90 minus theta. So let me call this alpha, where alpha is 90 minus this. So to write the direction, we'll call not alpha degree towards direction east. So come back to the diagram here. Come back to this diagram of the resultant. Draw a vertical which shows north, because we are going to start from this north. Then turn to the direction where you are going to be in contact with the resultant line. But you do not know this angle here, alpha. But total angle here is 90. So you're going to say 90 minus 21.7. So do that in your calculator. 90 minus 21.7, that's going to be the angle here, alpha. So the direction can be written like this. The direction can also be used in this format. Let me put it here.
68.3.
Thank you. 9.46 newtons. Okay, that is Newton. The first N is Newton. Then I'm going to look at the diagram. Not 68 point what? 68 point what?
68.3.
68.3.
Yes. What direction are you turning? Look at from the north now. How are you turning? Are you turning to this direction, or you are turning to this direction? You are turning to the left. The left is what? North, east, south, or west?
68.3 east.
Thank you. No, west. So the left is west. So you are turning to the west. So it's going to be north 60. I didn't get your value. 68.3. 68.3 degrees west. This is alternative way of doing that. So I believe this has clarified. This is the total risk. Now, thank you very much. This is the resultant. If you are now told to find the equilibrant, you are going to use the same value, because equilibrant and resultant have the same magnitude, but direction, sorry, I did not put not 68. So the opposite, this is what you are going to do now. So if it is resultant, that's resultant. If it is the equilibrant, okay, equilibrant, you are going to have the same magnitude. Please listen to this. 9.46 newtons. 9.46 newtons. What's going to be the direction? Change north. What's the opposite of north? South. Say south. The angle will not change. 68.3. We are going to show that in diagram now. What's the opposite of west? East.
East.
This is the equilibrant. Now let us show how south 68.3 degree east. If you are familiar with bearings and distances for mathematics, you will see that. Let us show that in diagram. Let's see this diagram now. For example, if this is the resultant, of a vector r, this is the resultant, okay, the equilibrant goes the other way, is directly in line, will be the same length, because they are of the same magnitude. This is E, equilibrant. Both of them are the same length. Let me use this cut to show that they have the same length. If resultant is 12 newtons, equilibrant is also 12 newtons. Now check now. If this is theta, from vertically opposite angle, look at this line, look at this line now. Look at that line. Theta. I'm cutting this line and this line. If I continue this, it's going to go downward. This is it. If I continue this, it's going to go in this direction. So what is the angle in between the two of them? The angle must be the same, theta. Now let us see how we can represent this. This is not. If you want to quote for this resultant, it's going to be not theta degrees to the east, to the line touching the resultant. You can see not theta degrees east, not theta degrees to the east. If it is the equilibrant, come and see. We're going to start from here. You either start from south or north. Okay, this is south. Theta degrees to what direction? West. This is west. You can see. This is the west. This is the west. So we're going to be south. What angle are you going to turn to the equilibrium? Theta degrees west. You can see. So just south, the same thing. Theta degrees west. Just change south and east. South for north, and then west for. So can we leave this now? And then I want to introduce equilibrium. So today we will not see some important calculation on equilibrium. We're going to go to also what's it called? Moment of a force. Okay, the turning effect of a force. So let's see equilibrium. In fact, should I just leave this equilibrium? This part of equilibrium is about reading. We want that you go and read up this. Let me write what you're going to read up. You can see this in your table, other equilibrium or stability. Stability. Either you see it as stability or equilibrium. Okay, so go and check for neutral equilibrium, stable equilibrium, unstable equilibrium. There are three categories of equilibrium. I'm mentioning them now. I want you to go and read more on them. Stable equilibrium, unstable equilibrium, and what? Neutral equilibrium. Stable equilibrium is easy. It's easy. Let me give you an example. Let me just draw these three things here. Look at. So this is a cone seated on its base. This is another cone seated on the apex. And then this is another cone seated along the slant height. Okay, rested along the slant height. Now, there's one hint I want to give you again. You read up this under stability or equilibrium. Stable equilibrium, unstable equilibrium, and what? Neutral equilibrium. If this has been theory exam like WAEC, what they usually ask you to distinguish from is what? Distinguish between unstable equilibrium and neutral equilibrium. Let me assist you with this. You're going to read up this. A body is in stable equilibrium. Really go and read up. I'm just mentioning. I'm not dictating. I'm not writing. I just want to listen. If on given a slight displacement, the body returns back to its original stable state back. For example, look at this cone here that is seated on the base like this. It is stable, it's balanced. But this cone here seated is not balanced. But if you insert it by using sand to hold it, just such as nail, this is a nail now. This is a nail standing like this. It is not easy, but you can pin it to a wood, or you can pin it to a sand. It will look stand. But if you push it, it's going to fall. It's going to fall this way. It's going to fall this way. You should not be resting like that. So when you give this what's it called? This cone seated on the base, you push this head a little up like this. Let me use dotted line to show how you displace it. You displace it like this, okay? So that this base opens up a little, opens up. You just push the head up a little so that the base open. You are saying what is under it. It's standing now like this now, like this. It's not standing like this, okay? Instead of seated like this, instead of seated horizontally. So if you leave it back, it's going to stand back. Is that not true? Please, response. It's going to stand. So this body is said to be equilibrium. So the definition is talking about when you give it a little displacement and it returns back to its original position. So that body is stable. But if you push this second cone that is standing on the apex, it's not easy to stand. You have to pin it on something. If it manages to stand, if you give it a push from here like this, if you give it a push from here, it's going to fall and slip like this. Is that not true? So a body is in a state of unstable equilibrium. If given a slight push or displacement, it goes to rest in a different position, using a different style. It was standing with its apex before. It will now be resting like this, such as this needle or nail. It should not be sleeping like this now. It should not rest like that. It's no longer in the standing position. So if a body is such in this position, it's said to be unstable. But if the body is naturally like this, then you give it a slight displacement, you roll it. It will not be in that position again. It will roll and go and rest in a different position. So a body is in a state of unstable equilibrium. If given a slight displacement, it goes further to rest in a different position. That one is on neutral equilibrium. So the distinction between them, I won't mention it again. I've stated it. For unstable, you give it a slight display, it changes
So
position.
what of neutral?
That's neutral is what I just mentioned now. It rolls on. Look at this cylinder, this cone. I mean, this cone. Even though it is cylinder, if it is cylinder like this, cylinder slipping on along its length like this. Okay, if you cause it to roll like this, roll. Okay, you push it like a drum. It will move further from where you kept it. It will now, when friction now acts on it, it will now stop in a different. That is neutral equilibrium. For the one for unstable, it will still be around that position, but it will just change. It is standing on an uncomfortable position before, like a needle pin to the ground, maybe to sand. It's not supposed to stand like that. A nail is supposed to stand comfortably by using the head and the pin pointed side upwards, such as this. This is supposed to be the most balanced state, but this is not a balanced state. So if you push it from this edge, you push it along this side, it will fall. It will fall and now slip like this, like this. So it does not move further away, but it falls. It changes its position, its position of resting by slipping on the side. So it is unstable. But if you are slipping like this, you now roll it. It will roll to a different place and rest. That is unstable. Unstable goes to a different position, but neutral equilibrium rolls and go and rest in a different position. But unstable, it just changes its style of resting. It was standing to with the pointed mouth before. Now it is sleeping because you pushed it. But if you push this a little slight push displacement, you open it up, you leave it, it returns back. Then property of bodies in stable equilibrium. Only
Yes,
object.
Stable equilibrium will return to its original position.
Yes, stable. It returns. Like, this is what I mean. This if this has been fed or using simulation, you will have seen it very well. This is a cone standing now. Normally, it's going to be in a state of stable equilibrium. It is resting very perfectly that way. Okay. Now, also, if I now push this head a little, such that this side opens, it now looks like this. I open the mouth, the bottom a little, like this. Okay, instead of it standing like this is the original standing position. Let me use dotted line. This is the original standing position. It's supposed to be seated like this, but I have now opened the mouth a little like this. So if I leave it back, it will return and sit back to that side. That is stable equilibrium. I want you to read up this. You might not see even this diagram that I'm showing you in textbook, but just know the definition, and I've shown you what you're supposed to see. It returns to its original equilibrium state. Now, I want to tell you property of objects that are in stable equilibrium. Okay, they have low center of gravity. Please read up CG, center of gravity or center of mass. Okay, that is the point. We're going to need this when we start movement. That is the point where the resultant mass or the resultant weight of an object appears to pass through. A body is made up of different tiny particles, as we have seen in molecular different, let me call it different masses. So they all have their weight. If the body is regular, if it's a regular body, such as a perfect square, the center of gravity is going to be at the exact midpoint. So there's going to be a mass. This is now the position of the CG, center of gravity. If you are calling it mass, we call it center of mass. If you are calling it gravity, center of gravity. So center of mass is the point within a body where the net or the resultant or the total mass of the body appears to pass through. So all the weight of the body appears to be at this middle point. But if the body is irregular, the center of gravity or the center of mass will be tilted to one side where more mass is. It may be to this side. So for regular body, for body that is in stable equilibrium, the center of gravity is low. That is why during sports, there is a sport known as Grand Prix.
So what do you say about center of mass?
Center of mass. I want you to read all this part. I want to go to calculation, but I'm still doing it for you. I've told you what to go and read. Open your textbook. Go and read about stable equilibrium, unstable equilibrium, and neutral equilibrium. I've actually taught it now. There's no calculation. I want us to leave that so that you are going to say it in your exam, in your test this week, please. Stable, unstable, and neutral. So what did you ask me now? Center of mass. I want you to go and read it up. It is the point within a body where the total mass appears to be concentrated. If you call it center of gravity, it is a point within a body where the total weight of the body appears to pass through or appears to lie. Okay, so now if this is then I'm mentioning racing cars, they call it Grand Prix. We don't have such sports in mostly this part of Africa. I think it's in South Africa, where cars they are moving with very high speed. You will notice that you cannot even bend. Look at like your normal car you have. You see that the tire is raised. You can bend and look from under the car and see the other side. But for racing cars, they bring them very, very low to the ground. It is to improve their stability because they are going to be bending around corners. So they should be stable. So bodies with very low center of gravity are stable. Look at this cone. I want to come back to this cone. I'm actually touching what I want you to read. The center of gravity is around this, closer to the ground. The CG. This is the center of gravity around here. So that's why if you turn it the other way, it is not stable because the center of gravity is in a high position. And the center of gravity is too high compared to the ground. So bodies with high center of gravity are unstable. Bodies with low center of gravity are very, very stable. So example is those racing cars. They are very, very low. So they are very, very balanced as compared to the one with high. So their center of gravity is very, very low. So please, let's go to, okay, since our time is going, let me just know that I'm taking this now. Then let me go to some other important. Now, I believe you know what is stable equilibrium, unstable equilibrium, and neutral equilibrium. I've told you that it's going to appear in your test. Please. So go and read further on it. There is no calculation there. There is nothing. Then go and also read about, let me write it here. Triangle law of force. Next thing we are going to is moment for our next week class. Please, I encourage you to read about it too. So it's going to be easy. The part is calculation. I won't leave any calculation for you, but go and read about moment. We are starting it next week. What are you supposed to read there? The definition part. What is moment? What are the conditions of equilibrium of coplanar forces? What is the principle of moment? All those definitions, talk part. Read them up. I'm going to ask you at the start of the question, okay, of next week class, not in exam. I've not taught it. So, but the calculation is going to be my focus. So it's going to be easy for us. This is how we are going. What we are going to be looking. Mr. Ismail will do the same thing to you. He has given you topics. So we'll encourage other teachers to. Next week topic, introduce it to the student by letting them know from this so that they read little about it. So the class is going to be easy. So I've given you mine. We are starting moment. All the discussion parts, go and know it. I'm going to start that class with questioning you. So everybody's going to. So go and read about this. Triangle law of force. Let me type instead. I can type. Triangle law of force. Parallelogram law. Okay. Triangle. Sorry. Why is this thing not allowing me to type again? Okay, triangle law of force, parallelogram law of force. Okay, triangle law of force, parallelogram law of force, and polygon law of force. What distinguishes between the three? Triangle law. Are you writing it down? I'm supposed to be able to type. I don't know why my system is not allowing me to type now. Triangle law of force, parallelogram law of force, of addition of forces, and then polygon. We are not going to look at polygon. I told you something again. I said a figure, a system of forces will be in equilibrium if a closed figure is formed. Look at this. Let me show you this, how to do this now. Look, everybody see this. There's a vector going this direction. Okay, there's another one going downward. Okay, there's one going upward, there's another one going downward, and then there's one going this way. Let me call each and every one of them F. This is F1. Okay, this is F2. And then this is F3. Okay, this is F3. Now, there is just one horizontal drawn here, just ordinary horizontal, and this is making angle theta with the horizontal. F3 is making angle theta with the horizontal. How can we use polygon law of force or reconstruction all of them? If a closed figure is gotten, I can start from anywhere. This is not a vector. This one, it is just horizontal line to show this theta. So we have vector F1. Look at them. First F1 to the east, F1 to the south, F2 to the south, and then F3 making angle theta degrees to the west. So I want to combine these three. I want to confirm whether they are in equilibrium. I can start from anywhere. If I start with F1, okay, now look at this. This is F1. F1. Let me put this arrow is now F1. Okay, where this head stop, that's where anyone I want to draw now, the tail must start from there. I want to draw this F2 that is downward, then draw downward from here like that. So this is its own tail and this is its own head. This is F2. F2. Now F3. How does F3 goes? Look at the direction of F3. This I've looked at it before drawing this. F3. F3 going that way, right? And I must start it from where I stop here. Yes, it's going to close. This is F3. You can see the three forces, they close. This is not the resultant now. Resultant, we are looking at two vertical forces. Well, the resultant we looked at before, we have horizontal and vertical. Okay, they are not closed. And I use resultants to close them. And I show you the direction of resultants. Okay, sorry, let me clean this arrow. Now, this is the direction of this. I can put the arrow in the middle. This one is downward. I can also put the arrow in the middle. And this is F3. I'm putting the arrow in the middle. Now, the three forces form a closed figure. That means they are in equilibrium. I could have started from anywhere. Let me look at the diagram again. I can start from the vertical one, F2. Maybe I have to start from here, F2. I'm starting from the one that goes vertical, which is this. I'm calling it F2. 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 Then I want to draw horizontal that goes like, look at the way the horizontal goes, sorry, which is F1. Where this one stop, put this one there. F1. This is F1. Then where this one stop, I'm going to start on that one. Look at the direction that this one goes. It goes like this. Yes, it's going to close them. This is F3. Yes, anyhow I draw it, F3. Okay, so now if we consider only two for vectors that are drawn like this, because they form closed figure, we say they are in equilibrium. So we can say that the line that completes the other two is an equilibrant of the two. So when a system of forces are in equilibrium, each one of them is an equilibrant of the remaining two. Now F1 is an equilibrant of F2 and F3. This is F3. Okay, F3 is the equilibrant of F1 and F2, because if you consider only F1 and F2, the vector that completes them is F3. So F3 is the equilibrant. If I consider F2 and this F3, then the one that completes them is F1. So F1 is the equilibrant of F2 and F3. If I'm considering F1 and F3, the diagram, the vector that completes it to form a closed figure, because forming a closed figure signifies equilibrium. So what vector brings about that closure? That vector is the equilibrant. So when three or more vectors or forces are in equilibrium, then one of them is regarded as the equilibrant of the remaining ones. It is not for only three vectors. We can have, if a vector is going like this is where polygon comes in. Another one is going like this. Okay, look at that. Then another one goes down. I'm just saying. Then another one goes this way. And then they end like this. If I ask you, this is F1, F2, F3, and F4. Are these vectors in equilibrium? All of you, are they in equilibrium?
No.
No. Why? Why are they not in equilibrium? No closed figure form. If I draw a single vector to close this becomes a polygon. If something closes it like this, then this vector that brings about the closure is the equilibrant of 1, 2, 3, and 4. So this is 4. So I'm calling this one 5. So 5 is the equilibrant because it brings about closure. So equilibrants always go in the direction of all the vectors. They are going like this. It continues like that. It continues like that. No bending, no turning back. Then equilibrium goes in that direction. But resultant goes in the opposite direction. This, if I draw it like, because resultant and equilibrium are the same, it is their direction that differ. Resultants always counter the direction the vectors are turning. If vectors are turning this way, in that arrow, and that one turning this way, in that arrow, Then if this one also goes like that in that arrow, now this one that I draw here, is it resultant or equilibrium? Look at the arrows. Arrows should make you know. This arrow goes like this arrow goes like this, and this one follow them to go like that. So that last one that I draw here, this number 3, is it resultant or equilibrium?
Resultant.
Result.
Okay, who is saying resultant? Your okay, let me call your names. Let me see who is still here. Okay, Mazida. Let me go back. I've seen all of you. You all stay here. Mazida, is that resultant or equilibrant? Mazida, she's not
Sir,
talking. Resultant?
yes.
Okay. What's her name? What's the other lady? What's the Mariam? Is this resultant or equilibrant?
Equilibrant.
Uzain, resultant or equilibrant?
Resultant.
Dean, resultant or equilibrant?
Equilibrant.
Mustafa, resultant or equilibrant?
Equilibrant.
Now, who is left, please? Mention your name. Who is left? Do I have somebody left? Not mention. If Olamide, please, I'm apologies. Is this anything? Have you all spoken? Have you all spoken? Everybody has spoken. Now, those that call it equilibrant, what was your reason? Let me call only one. Dean, what did you call it?
Equilibrant.
Why is it equilibrant? That is the reason. Mazida and whoever that call it equilibrant, I call it resultant. It is not resultant. Resultant will go against the direction. Something is going like this. Look at something is going like. As it goes like this, then this one now counters it and goes backwards to the direction. Then that is the result. Resultant counters the direction all the vectors are moving. Now look at something starts from here and it goes like this. Look at the arrow. Then the arrow, it turns like this. It goes like that. The arrow, it does not counter it. Then this one sounds to continue in the direction. It's like you going in your house. You move to the left and goes to another direction without turning back. If you turn your back to move to the backward, then that's where a resultant comes in. This arrow has not turned back. It's still arrow like this. It's still arrow going like this, and the arrow follows like that, like that. Okay. If it has been resultant, it would have turned back like this. It would have turned back. It will not go in their direction. So that is the distinction between equilibrant and resultant. Now look at this arrow. This arrow going the same, going like that as well, going downward, then going to the east, and then going upward. Let me clean this. Let me clean this one that goes down. Going upward. Oh. Going upward. So when the equilibrant has been drawn, it is a final vector that brings about the closure. That's why they are in equilibrium. So if we ignore this as if it is also part of the vectors, this one that I say is their equilibrium. If I ignore it and I say that's where I'm starting, then I draw this next, I draw this number 2 next, I draw this next, and I leave it. Then this one is one that brings about closure. Then it becomes the equilibrant. If I leave that again, I say I'm starting from 3 and then go like this and then go upward and then stop here. Okay, then this one that completes it is the equilibrium. So when a system of vectors are in equilibrium, any one of them is the equilibrant of the remaining one. This first 3 is the equilibrant of 4, 5, 1, and 2. 2 is the equilibrant of 3, 4, 5, 1. 1 is the equilibrant of 2, 3, because if we ignore 1, if I cancel 1 from the diagram, then 1 will be the one that will bring about the closure. So it's the equilibrant. You can see. So any one of the vector is the equilibrant of the others. Is that clear now? Please, what did I ask you to read of, even though I've mentioned it? Read about center of gravity or center of mass. Stable equilibrium, unstable equilibrium, neutral equilibrium. even as I've dealt with it. Let me show you a diagram. Look at this bowl. Look at this bowl. All of you, look at this bowl. And a ball is inside this bowl like this. If a ball is inside this bowl, if I pick the ball, this is the ball. I remove it from there and I put it at this edge. All of you, what will happen to the ball? If you
It's
go
a-
dangling, and be dangling and dangling, and later when you want to come back to rest, where will it be? Will it rest at the edges or in the middle where it was?
At the
In the
middle.
At the middle.
In the middle.
Now, what kind of equilibrium is that? What kind of equilibrium is that? You go back to where it belongs.
Stable equilibrium.
Stable equilibrium. Thank you very much.
Equilibrium.
Thank you. Now, what about this? What about this? I turn the bowl upside down. I put a ball here and I push it a little. What will happen to the ball?
It will be
It will
unstable.
come,
Change its position.
and then will it stop here or will it still be rolling on the floor a little to one side?
will
It will still
stop
be rolling
there.
now. No, listen, no. Will it stop when it gets to the edge of the bowl or it will still roll a little further again?
You still roll a little further.
What kind of equilibrium is that? I'm
Unstable.
not going to tell you anything.
Unstable equilibrium.
You say what?
Unstable equilibrium.
Unstable.
Unstable equilibrium.
Go and read. Go and read. We'll way it rolls further away, it continue moving, such as a cylinder rolled along its slant height. Okay, so please, if it is white, I don't know whether anyone of you is right for the stable equilibrium is easy. They ask you to distinguish between unstable and stable. So you first of all introduce the definition. So go and read up on that. And then how do you answer the distinction? How do you differentiate between unstable and neutral equilibrium? Go and know that before next class. I'm going to ask you those questions. And then I believe I've already taught you, because you may not see this in this explanation in textbook. You just see definition and you may not clarify both. Okay. So I think we are going to end this class now. And then is anybody having challenges with the calculation of what we look? I'm going to, in fact, let me leave this exercise for you, all of you. Before you go, make sure you draw this and then find me. I'm going to look for that jam. A student send it to me. One of my students I'm checking online on also jam. I'm going to open that password. Open password. That's what she does.
Mr. Lukman, inshallah, I'm going to send them questions too.
Thank you. There's
Part of questions, yes,
Please.
I will snap and send to
In
them
fact,
so that they can practice with it.
Aisha always bring questions to me because she opens that password. If you have learned something, she goes to Bio to look for students. Please, it is open to you. It has to be discussion that has to do with academics. Please. Thank you very much. Thank you very much. I'm leaving you with this problem. Please make sure you draw this. This is 30 newtons. I'm going to give you the value of angle that you may not need, so you use alternative. This angle is making 40 with vertical. It's left for you to decide what to use. And then this is 18 newtons. 18 newtons. This guy is 12 newtons and this 15. Okay, there is this boy here as well, making angle 60 with horizontal. Oh, sorry, I did not put a force here. 17 newtons, 20 newtons. Listen to the question now. This is what I want you to find actually. So when you are solving this, notify me. This is what I actually want to find: the net vertical force. Find the net vertical force. That is the actual question. After you have done that, the B part is find the resultant force. A says you should find the net vertical force. I'm supposed to be able to type now. Okay, yes. Find the net vertical force. Okay. And B says, this is B part, saying find the total resultant of all the forces. Oh, sorry, that find is not correct. Find the total resultant of all the forces. Oh, it's moving beyond where I sent it. So have you seen the question? Put this down. Why is this moving beyond where I'm putting it? Okay, this is fine anyway. Okay, find the total resultant of all the forces. Okay,
Sorry, sir, Mr. Lukman.
Sam.
As that is ongoing, I want to inform them
Okay,
that they are very lucky for being here because they are getting these things qualified teachers with high level of experiences. So
now,
I want them to make the best use of this opportunity because they might not see it again.
yeah.
So all things given to them, they should make good use of it. For example, the assessment
But,
correction that
okay.
was sent by myself and Mr. Lukman. Please, you guys should review it. It's going to be helpful for your next assessment.
I want to even, okay, I'll do that this evening. The
Okay.
second test
Yes,
assessment.
because your compilation of question is not only meant for the things you are doing as at now. Things that you've done before, like week 1, week 2, there are compilations of what you'll be seeing in your week 3 assessment too. So make good use of that. Then secondly, I want to implore you to inform your colleagues and your friends too that you feel want to write UTME examination. Please, it's never too late now. They can still join us before we become too saturated or the time becomes so close. So the closer you are to the UTME period, then the lesser the chance of having a good grade. But the earlier the better. So you can still implore others, maybe your family, friends, or colleagues, to join us. We are going to roll out the end of this month very soon. By next month, we'll be starting again another month. So that's the piece of information I have for everyone. Thank you for listening. Have a nice
Yeah,
day.
thank you very much. Thank you, Mr. Ismail. So I asked you to read about neutral, unstable equilibrium, center of mass slash center of gravity, equilibrium law of force, triangle law, parallelogram law, and polygon law. Polygon law is what we apply here. When the vectors are more, we call it polygon law. That's just the distinction between polygon and, but when they are just two forces, we use triangle law and parallelogram law. Parallelogram law, triangular is an extension of parallelogram law. So when they are many, you can see one, two, three, four here. So we call it poly. This is a polygon now. So that's when we use polygon. But I'm just only showing you this. You don't need this for just to bring additional explanation. JAM does not cover this aspect. It's just either parallelogram or parallelogram law or triangle law. Okay, so put this diagram down and then read up what I asked you to read. And then I said we are starting moment. All the discussion part of moment, please prepare for it. I'm going to ask you question on it and all this, and then we start next class with calculation straight up. Okay. What we need is okay, don't worry. So that's what. So read up all the principle of moment, condition of equilibrium of parallel coplanar forces. What do we mean by parallel coplanar? Parallel coplanar forces. Look at the word parallel, coplanar. Don't bother yourself about the coplanar. Sometimes you can call it coplanar. CO, then planar. Sometimes we bring English into play. When you see this word co, what does that mean? Like your colleague, somebody somebody that is doing something together with you. Maybe your friends at work is your colleague, your your co-worker. You are doing something together. So when vectors are parallel, number one, parallel coplanar forces. They are parallel. You know the meaning of parallel. They are going in the same direction. Look at this. They are parallel. Even though this is pointing up, this is pointing up. Even this third one is pointing down. They are still parallel, just that the direction of the third